बिस्मिल्लाहिर्रहमानिर्रहीम सल्लल्लाहु अलैहि व आलिहि वसल्लम अल्लाहुम्मा रब्बि ज़िदनी इल्मा सल्लल्लाहु अलैहि व आलिहि वसल्लम आमीन अल्हम्दुलिल्लाहि रब्बिल आलमीन. In this video, I will be covering the key concepts from the complete S2 syllabus in a structured and concise manner. The aim is to help you revise effectively by refreshing, summarizing, and organizing the most important topics. I highly recommend that you watch the lecture until the end to gain maximum benefit. This session is designed to support your final revision and strengthen your understanding of the subject. We will begin with the Poisson distribution, followed by linear combinations of random variables, continuous random variables CRV, sampling and estimation, and finally hypothesis testing. Wishing you all the very best for your exams. Let's begin. So, discrete probability distributions, binomial, geometric, and Poisson. We won't do geometric distribution. We have to do binomial and Poisson in S2. And discrete means countable quantities. For Poisson model, the events occur singly, computer breakdowns like the number of emergency calls, with a specific unit, average at a constant rate. The conditions of Poisson distribution model. Events occur singly, randomly, independently, and at a constant rate. This is the way to describe the Poisson distribution. X is Poisson with average lambda, mean lambda, and this is the only parameter of the distribution. Lambda is the mean, average, or rate. This is the formula of Poisson distribution. You can get this from MF19 as well. Make sure you use MF19 wisely. Keep it with you while practicing so that you are used to with MF19. Poisson variable is discrete and it takes these values from 0 to infinite. Therefore, Poisson distribution is an infinite distribution. The mean of Poisson is lambda and the variance is also lambda. Therefore, mean is equal to variance is equal to lambda. So, if any distribution has same mean and variance, it can be modeled as Poisson distribution. To make calculation simple, probability x0 we write e minus lambda, and for 1 lambda e minus lambda. We got these results through this formula. How to find x greater or equal to 3? We write 3 to infinite. Then obviously we can't find this, so we have to use indirect method, 1 minus numbers which are not in this list. This starts from 3. This is the direct method and this is the indirect method. In Poisson we always use indirect method, but we write direct method so that we can write these numbers correctly. We write those numbers here which are not in this list. We take e minus lambda common, so this is the way we find this probability. 1 minus e minus lambda. For 0 we write 1. For 1, lambda power 1 over 1 factorial, lambda square over 2 factorial. The random variable x has the Poisson distribution. State the values of x can take. X takes value 0 to infinite. And this is an equation, the given equation, and we need lambda. So for x1 we write lambda e minus lambda. Copy 3. For x0 we write e minus lambda. Cancel these two and get the value of lambda. This part is simple, I'm leaving this. Make sure you always check the unit of lambda. The number of calls received at a small call center has Poisson distribution with mean 2.4 calls per 5 minutes. So write 2.4 for 5 minutes. We need probability exactly 4 calls in an 8-minute period. So get the value of lambda for 8-minute period. Do cross multiplication. This is the value of lambda, 3.84. Now get this probability x is equal to 4. And make sure you always write your non-exact answers up to 3 significant figures. This part is important, so let me discuss this complete question. The number of accidents on a certain road has a Poisson distribution with mean 0.4 per 50 days. So 0.4 is for 50 days and we need for 365 days, which is 2.92. Fewer than 3 means less than 3, so 0, 1, 2. Write e power minus lambda here for 0, 1. For 1 write lambda power 1. For 2 write lambda square over 2 factorial. And make sure you give your answer up to 3 SF. This is an important part. The probability that there will be no accidents. No accident means probability 0, which is e power minus lambda. During an n days is greater than 0.95. See, 0.4 is for 50 days. For n days, lambda is 0.008n. Now use this given information. Write e power minus lambda here, copy this. Now take ln on both sides. Lambda is 0.008, ln is 1, lambda is 0.008n in fact. Now get this probability, get this in decimal form. See, both are negative, so while cancelling negative signs, change the sign of inequality. We need the greatest value of n. The greatest value is 6. You can also draw the number line. 6.41 is here. So the greatest integer value is 6. The sum of two independent Poisson distributions. So we have two Poisson variables and x is Poisson with mean lambda 1, y is Poisson with mean lambda 2. We need x plus y. We just need to add their lambdas, x and y's. Care must be taken regarding the value of lambda according to the given intervals. Use ratio method for the value of lambda. We have done this. Okay. Question 25 from this here. 2 ponds A and B each contain a large number of fish. It is known that 2.4% of fish in pond A are carp. So 2.4% are carp, 1.8% in B are carp. Random samples of 50 fish from pond A and 60 fish from pond B are selected. So get the value of lambda. So this is basically a binomial model. For pond A, you can write a binomial with P 0.024 and 50 here. So binomial models, two binomial models, get lambda using NP. So this is NP. Pond A binomial distribution 50.024. Pond B is also follows binomial with n60 and this is 0.018. So with the help of mean NP we can get lambda. Now the first part, use appropriate Poisson approximation, right? The samples contain at least 2 carp from pond A and at least 2 from pond B, and means multiply. At least 2 we write 1 minus 0, 1. This is here for A and this is here for B. And this is up to 3 significant figures. The samples contain at least 4 carbs altogether. So first add the values of lambda. So this is lambda. At least 4, write 1 minus 0, 1, 2, 3. This means total. Approximations. Poisson approximation to binomial model. Conditions. When n is greater than 15 binomial and p is less than 0.1, or if n is greater than 50 and np is less than 5, then we solve binomial distribution question by Poisson distribution. Since this is the conversion from discrete to discrete, so no continuity correction is needed. We just need NP, mean. Here is the question. In the data entry department of a certain firm, it is known that 0.12% of data items are entered incorrectly. So this is P of binomial. And this is N. A random sample of 3600 data items is chosen. The number of these data items that are incorrectly selected is denoted by X. State the distribution of X. X is binomial with parameters N, and this is P. State an appropriate approximating distribution. So appropriate approximating distribution is Poisson with mean 4.32. This is N, this is P. Justify the use of your approximating distribution. So N is 3600, which is greater than 50, and P is this, which is less than 0.1. Make sure you show the comparison, otherwise you won't get the mark. We need X greater than 2. This is so simple. It should be, through direct method, the numbers are 3 to infinite. So 1 minus numbers which are not in this list, 0, 1, 2. And the answer should be up to 3SF. One more question of binomial to Poisson. The booklets produced by a certain publisher contain on average 1 incorrect letter per 30,000. So this is P, 1 upon 30,000. And these occurs randomly. And this is N. So this is the binomial distribution. Get NP, which is 5 upon 12. And we need this probability, at least 2 errors. So for at least 2, write the direct method, 2 to infinite. In indirect method, 1 minus numbers which are not in this list. And the answer should be up to 3SF. Normal approximation to binomial distribution. We did this in S1. This is just for a revision, and we will use this concept in hypothesis testing as well. So we use this in S2. This is the condition for approximation. Both NP and NQ are greater than 5. This is the normal distribution, and when we convert this in normal approximation from binomial, then we replace mu by NP and sigma square by NPQ. And this is the formula of Z with continuity correction. X plus minus 0.5 minus NP divided by NPQ under root. For continuity correction, use number line. Now, normal approximation to Poisson distribution. Simply Poisson to normal basically. This is the condition for the approximation. Lambda must be greater than 15. So we replace mu by lambda and sigma square by lambda. Since this is discrete to continuous, so we have to do continuity correction. And for that we use number line. This is the formula of Z. X plus minus 0.5 minus lambda divided by under root lambda. Okay, number line. If we have to find this probability, so we mention the first inclusive integer. The first inclusive integer is 50. Mention this on number line. Since we are going on right side, therefore take the lower bound of this number. In number line, if we go on right side, take the lower bound. If you go on left side, take the upper bound of the number. So the number is 49.5. So we will solve this with 49.5 minus lambda divided by under root lambda. Now see, the next is greater than 50. So first inclusive integer is 51. Mention this on number line. Since we are going on right side, take the lower bound, 50.5. This is mentioned. First write the inclusive integer and then take the lower bound. Here take the upper bound. So first inclusive integer is 59 because this is exclusive. So 59 write 59 here. We are going on left side, take the upper bound. This is the way to solve normal approximation to Poisson distribution. Here first inclusive is 41, last is 70, mention both on number line. Here we are going on left side, so take the upper bound. Here we are going to right side, take the lower bound. Okay, just one question I will discuss so that I will go to the next chapter. The number of inquiries received per day at a customer service desk has Poisson distribution, single event with mean 45.2. If more than 60 inquiries are received in a day, the customer service desk cannot deal with them all. Use a suitable approximating distribution, which is normal approximation, to find the probability on a randomly chosen day the customer service cannot deal with all inquiries that are received. So more than 60 they cannot receive. So more than 60 means first inclusive integer is 61. This is here. We are going on right side, so take its lower bound. 61's lower bound is 60.5. This is lambda 45.2. This is greater than 15. That is why we are using normal approximation. Now convert this statement into z. 60.5 is here, lambda is here, and under root lambda is here. From here, use your S1 concept. This is small area, so 1 minus 5. And answer should be up to 3SF. Well, this is all from Poisson distribution. Next chapter is linear combinations. Okay, in linear combinations of random variables, we must know the properties of mean and variance. So mean of constant is constant, like E5 is 5, because all observations are same, so mean is also same. So mean of constant is constant. If something is multiplying with variable like coefficient A of x, then you can write this outside the bracket. You can bring this outside. So it would be AEX. For example, if each observation is multiplying with 3, a same constant, just multiply mean by constant instead of finding the new mean by adding all. So if all observations are multiplying with same constant, just multiply mean by same constant and get the mean of the new observations. So this is the property. So E5x is 5EX. When we combine these two properties, we get this property AX plus B minus also. In mean, signs remains same. So it should be A times EX plus constant, because mean of constant is constant. So in mean, signs remain same. Variance. If all observations are same, then there is no variation, so variance is 0. So variance of constant is 0 because no variation. Since A is coefficient of x, A is multiple of x, so when we bring this outside the bracket, we have to square it. This is the property of variance. So write 3 square here. So when we combine these two properties, we get this property next, C. So A square Vx and variance of constant is 0. So 5x plus 3, 5 square Vx and variance of 3 is 0. In variance, signs always positive because variance can never be negative. So convert negative into positive. Properties of expectation and variance. With this example, if one variable x is added to 3 times such that x plus x plus x, then the mean can be written as e x plus x is equal to e 3x. Since this is coefficient, bring this outside the bracket, 3ex. For variance, 3x, 3 times of x, right? So when you bring this out, must square 3 square vx. Whenever we bring coefficient outside the bracket, we square it. That's it. Because coefficient is multiple of x. It's mentioned. One variable x is added to 3 times. So 3x means 3 times x. Next case. In the case of sum of 3 independent observations, we are adding 3 independent observations, or we are taking the sum of 3 independent observations of x. So mean of these 3 observations, this will become ex1, this will become ex2, this will become ex3, and all are equal to ex. So ex will become 3ex. So if you are adding 3 independent observations of x, write like this, 3ex. Don't write this as, this is the wrong way. The sum of 3 independent of observations should be written like this, 3ex. In variance, x1 plus x2 x plus 3, add the variance of this, vx1, vx2, vx3. So we have all are equal to vx, so 3vx. Do not square this 3 because we are finding the variance of sum of 3 independent of observations of x. So 3vx. Here is the summary. If x is added to 3 times, x plus x, write e bracket 3x, this is the coefficient of x, 3ex. In variance, 3x, so when you bring this 3 out, it will be 3 square. Why? Because this 3 is multiple of x. x1 plus x2 plus x3, sum of 3 independent observations of x. So it should be 3ex. And this should be 3vx because we are adding variances of these 3 observations. Okay, this question. The masses in kilograms of large sacks of flour and small sacks of flour have the independent normal distributions. Find the probability that the total means sum, mass of 6 randomly chosen large sacks, so L1 plus L2 plus L6 is more than 245 kg. See, L1, L2 till L6. So basically when we will find the mean of this, we will write 6 EL. So 6 times mean of EL, which is 40. So 240. Same with variance, 6 VL. And we need more than 245. Now convert this statement into Z. Copy this 245 here, mean here and variance here, under root. And you know how to deal with this. Small area, so 1 minus 5, 3 significant. Now this part is important. Find the probability that the mass of a randomly chosen large sack of flour is less than 4 times, 4 times multiple of small sack of flour. So L is less than 4S. And this 4 is multiple of S. Now first bring this on left side. L minus 4S. Now take E with this. L minus 4S. So this will become EL and this will become minus 4ES. That's the mean. Make sure when you find variance of L minus 4S, you should write VL, convert this negative into positive because variance is always positive, and this 4 is multiple of S, so must square this 4. That's the variance. Now convert this statement into Z. So 0 minus mean divided by standard deviation. This is phi and the answer up to 3 SF. This is an important question, but let me first explain the concept. This concept. See, if we have modulus A less than A, so we remove modulus in this way. Z lies between minus A and A. This area is required. So if we have this, remove modulus in this way. If we have greater sign, remove modulus in this way. This area and this area, both are required. So Z less than minus A, this one, and Z greater than A. This is 1 minus phi A, 1 minus phi A. So 2 times 1 minus phi A. Now this question is very important. Let me discuss the whole question. The heights of buildings in a large city are normally distributed with mean 18.3 and standard deviation 2.5. So H is normally distributed, mean 18.3, variance 2.5 square. Find the probability that the total height of 5 randomly chosen buildings in this city is more than 95. So H1 plus H2 till H5 is greater than 95. So we have 5EH. When we will find mean of H1 till H5, we need to write 5EH. This is here. So 5EH. And this is 5VH. Now write 95, mean is here and standard deviation is here. This is variance, take the square root of this. So this is 1 minus phi, small area. Now this part is very important, this one. Find the probability that the difference, whenever it says difference or differs, either difference or differs, always use modulus. Find the probability that the difference between the heights of 2 randomly chosen buildings, meaning H1 and H2, in this city is less than 1 meter. Make sure you must write this as H1 minus H2 modulus less than 1. Because of difference or differ, use modulus. You can also write H2 minus H1. Either H2 minus H1 or H1 minus H2, no problem. Now remove the modulus in this way, as I told you. If we have lesser sign, then write h1 minus h2 between minus 1 and 1. Now get the mean and variance of this. So h1 minus h2, the mean is 0, and h1 minus h2 variance, add sign, replace negative by positive, and this is the variance. Now convert this statement into z. So z minus 1 is here, mean is here, and this is the standard deviation, same as here. This is phi, this is 1 minus phi, and that's the final answer. To be good at this topic, you should watch my lecture on LCRV, the complete lecture. I explain everything in detail, the concepts, and I did practice questions as well. Now the next chapter is CRV. Okay, we start from here. PDF of a fixed value, constant value, particular value. If they ask find PDF x is equal to 3, it is always 0, because when we integrate it, the limits are same. So it's 0. The probability that CRV is equal to a particular value is always 0. In this chapter, these signs mean same thing. It's continuous variable, so no problem with these signs. Either write like this, this is inclusive, or both inclusive, no problem. For all, the formula is this: lower limit, upper limit, fx dx. Area all x fx dx is 1, because total probability is always 1. If we need this area, this will be 1. Okay? And if we need between a and c, write like this: a lower limit, c upper limit, fx dx. If we need more than c, this one, so this is lower and this is upper. So this is lower limit and the upper limit is given. Less than means upper limit, and lower limit take it from the function. If we need this area 2 to 5 probability, then break it this into 2 to 4 and then 4 to 5. Work for this, integrate this, and this is 0, because outside 4 is 0, less than 1 is 0. We use this formula to find the constant, and all x means lower and upper limits. For mean, we use this formula x fx dx. This has power 1, so this has power 1. For variance, we first need ex square. This is 2, so this is 2. And this is the formula of variance: ex square minus ex whole square. This is available in MF 19. If ex is 2 and ex square is 10, then substitute 10 here and 2 square here. This is variance, and its square root is a standard deviation. Median, quartiles, and percentiles. For median, this is upper limit, lower limit, and median is 50%. So write 0.5 here. For Q1, upper limit Q1, lower limit given from the function, and Q1 is 25%. So write 1 upon 4 or 0.25 here. For Q3, write Q3 here, lower limit here, and this is 75%, 0.75. For percentile, P90, let's suppose this is R. Write this R here, lower limit 90%. And this is IQR, Q3 minus Q1. We sometimes use this formula, area of similar objects. Like in this triangle, these two triangles are similar. So this is the larger triangle, this is the smaller triangle. The base of this small is m, whereas the base of this large triangle is 2. The area of large triangle is 1 and area of this small triangle. Since this is median, so this is 0.5. Less than median 0.5, greater than median 0.5. So we can use this thing, area of small divided by area of large, length of small which is m, length of large is 2 and this area is 1. So AS, this is also given 0.5. So 0.5 small, 1 large, length of small m, length of large is 2, just square this and get the value of m. This is here. Alright. In increasing upwards PDF, median is closer to upper limit. Median is close to upper limit because of high density of observations. In these types of curves, standard deviation is highest or greatest because high density of observations at extreme sites. Because more probability at both extremes. The density of observations is high on extreme sites at both extremes. Here standard deviation is minimum. Why? Because density of observation is high. I mean most of the observation or large number of observations are close to mean. Alright. Next, let me discuss one or two questions from CRV. You should watch my lecture on CRV as well. Important questions of CRV. Okay, let me discuss this question. This question is important. 18. A random variable x has probability density function. Fx is a straight line segment parallel to x-axis, x0 and a. This is here 0, a. And outside 0 is 0, outside a is a. This is a rough sketch. Where a is a positive constant, so right side. State in terms of a the median of x. This is the lower limit, this is the upper limit, this is a straight line, so uniform distribution. So take the average of these two, a upon 2. By the way, this is the mean, median, mode, all are same. In symmetrical graphs, all are same. As in normal distribution, mean, median, mode, all are same. So median is a upon 2. Just take the average of these two. I did this in a different way, but this is the easiest way. Median is the average. It's a upon 2. I use area method, but this method is simple. X greater than 3 upon a. So this is so simple. 3 upon a means 75%. You can write this as x greater than 0.75 a. So this is 50%. Right? Half a means 50%. So this is 50, this is 100, so its average is here 3a upon 2. So this is 75%. What should be the probability? This is 0.5. Since both are same, 0.5 is divided in equal parts, so 0.25 here, 0.25 here. So this probability is 0.25. Greater than 0.75a is 0.25. Variance. Mean is a upon 2. I told you this is mean, median and mode, all. For variance we need ex square, and for that we must have equation of fx. So this height is 1 upon a. This is here. Use area formula and get the height 1 upon a. So the equation of this line is 1 upon a because this is in y-intercept. So fx is 1 upon a. X square is the formula part. This is the part of the formula. Now just integrate this x square and bring this outside. So this is x cube upon 3. Apply the limits 0 and a. So it's a square upon 3 ex square. And the formula of variance is ex square minus square of mean. That's it, this is variance. Another important part. X less than b is p. See, x less than b is p and b lies between these two. This is a upon 2. Okay. And it says b is between these two. Now we need what? This is an example. You can just skip this. This is here. The solution is here. So first check B lies between 0 and a upon 2. This is here. So mark B or label B. Between 0 and a upon 2, anywhere between 0 and a upon 2. Okay, so this is B. Okay, now its probability less than B is P. So this total probability is P. This. Okay, so this total is P. So what about this? See, this total is 0.5. So this should be 0.5 minus p. Okay. Now we need what? We need x greater than b upon 3 and a minus b upon 3. Let me copy this. We need this area. This is B and we need 1/3 of B. So this, divide this in 3 parts. 1, 2, 3. See, 1, 2, 3. So this total is P. So this should be P upon 3. See, P upon 3, P upon 3, P upon 3 makes P. So this is P upon 3. Because of symmetry, this is also P upon 3. And this width is B upon 3. If I say this width is 2 units, then what should you write here? A minus 2, right? Since this width is B upon 3, so write this number as A minus B upon 3. Now we need this area. This area. This is so simple. This is 1 minus this and this. So 1 minus 2p upon 3. Check this solution again. Here we have to prove, this is last question of this chapter, then we will go on to sampling and estimation. Move on to sampling and estimation in fact. We have to prove Ex. The formula of Ex is x fx dx, all x. So all x 2 and 4. Just integrate this and get the value of mean. We need variance. For that we need Ex square first. And the formula of Ex square is all x square fx dx. So all x 2 and 4. Multiply x square with this. So 4x cube minus x4. Integrate this, get Ex square. And the formula of variance is Ex square minus Ex whole square. Leave your answer in fraction. Now the next chapter is the most important chapter, sampling and estimation. Wait for 1 minute, then we will move on and we will continue. Just take a 1 minute break. If you find this video helpful, do share it with your friends so they may benefit from it. Now sampling and estimation. We have done these conditions for normal approximations. Normal approximation to binomial, both NP and NQ greater than 5 are greater than 5, do CC as well. Normal to Poisson, lambda is greater than 15, do CC as well. Poisson to binomial, n greater than 50 and p less than 0.1, n greater than 50 and np less than 0.5. You can write either from these two, either one from these two. Now CLT. CLT is applied for non-normal populations and sample size is greater or equal to 30. So if samples are taken from non-normal population and for large sample size, say n is greater or equal to 30, according to CLT, x bar is approximately normal. This is CLT. X bar is approximately normal with mean mu, variance sigma square over ns. Don't apply CLT if population is normal. Okay, sampling methods. Simple random sampling. This is the theory part. Simple random sampling means sampling without replacement. If the unit selected at each draw is not replaced into the population before the next draw, this is known as simple random sampling. And there are two methods. Drawing lots, random number sampling. Simple random sampling means sampling without replacement, and in this way or in this method every element has an equal chance of being selected. Now drawing lots is suitable for a small size of population, and you just need to learn these three things. You just need to write this. If they ask select a sample by drawing lot methods, then just write the first point, name all the members. Make sure you write name. Put the names in a bag or container. Select the sample of the required size. That's it. The accuracy of the information depends on sample size. If sample size is large, the information is more precise. Random number tables method. In random numbers, write these points. Number all members. If we have population of size 30, then generate 2-digit numbers from 0, 1 to 30. You can also write 1 to 30. If the population size is 300, then generate 3-digit numbers from 1 to 300. 0, 1, you may also write this 1. So first point, second point, third point. Ignore repeats. Ignore numbers greater than the size of population. Select the sample of the required size. Now, examples. See, describe briefly how to use random numbers to choose a sample of 10 students from a year group of 276 students. First point, number students from 1 to 276. You can write 001 or 276 or 1 to 276. Both are fine. This one is better. Generate 3-digit numbers. This is the second point. Ignore numbers greater than 276. Ignore repeats. That's it. Just write these 4 points. Number students from 1 to 276. Generate 3-digit numbers. Ignore numbers greater than 276. Ignore repeats. This is the way to select sample by using random numbers method. Okay, if random numbers are given, how to select the sample? A residents association has 654 members, numbered from 1 to 654. The secretary wishes to send a questionnaire to a random sample of members. In order to choose the members for sample, she uses a table of random numbers. The first line in the table is as follows: 1096, 4357, and so on. The numbers of the first 2 members in the sample are 109. This is the first one. The numbers second is 643 and the size is 654. Okay. Find the numbers of the next 3 members. So the next number is 573. This is fine. This is in the range. The next number is 765. This is outside the range. Just cancel this. The next one is 043. You can either write 043 or 43. Both are fine. Then 109. 109 is the repeating number. This is here. This is already selected. Then 289. So this is here. 573, 043, 289. Both are correct. 43 or 043. Sampling's advantages. It is less time consuming, it is cost effective, it does not destroy the population. Population disadvantages. It takes too long, more time consuming, expensive or cost ineffective, testing of all objects, testing of all items involves destruction. Testing may involve destruction. Not all population is accessible. If population is of size infinite or very large, then not all population is accessible. Okay, symbols used in sampling. Capital X means population, mu means population mean, and this is population standard deviation. Distribution of sample means, sample mean is x bar and sample standard deviation is s. This is population. X is normally distributed with mean mu, variance sigma square, and observations are more scattered from their mean. Sigma square is large, more variation. Population values are more scattered from their mean. Sigma square large, mean peak of the normal curves is low. Distribution of sample means. These are sample means, x1, x2, x10, all are sample means. Obviously, sample means are more close to population mean, and that is why we have a small variance here. The variance of distribution of sample mean is sigma square over ns. Ns means sample size, and it has a high peak. Why? Because sample means are more close to the population mean than the original population values are. This is the graph of sample means. Means are close to mu, are more close to mu. And this is the graph of the population values. There are more variation. Observations are more scattered from their mean. So this is the way to write population, and this is the way to write distribution of sample means. You just need to divide sigma square by ns. And that is why variance of sample means is less than variance of population mean. This is an important question. If both are known, if sigma cap square, the unbiased estimate of population variance, and true population variance, if both are known, then use the smaller of the two, as it has less variation and is therefore more accurate. This is an example. See, the unbiased estimate of population means is 0.523, whereas the true population variance is 0.55. This is the unbiased estimate of population variance, and this is the unbiased estimate, this is the true population variance. See, this one is smaller and this one is larger. So in later part, we would use this. See, 0.523. We already have done this. X is normal, we write in this way: population mean, population variance. Distribution of sample means, we write x bar like this. We just divide sigma square by ns for x bar, and this is the formula of z. X bar minus mu divided by this under root. Now from here, sampling is very important. The distributions of sample means. The distribution of sample means, case A, the distribution of sample means when the population is normal and sigma square is known. Well, when population is normal and sigma square is known, then for any sample size, see, for any sample size, the distribution of sample means is also normal. Mu sigma square over ns. Please try to understand this very carefully. If population is normal with sigma square is known, then for any sample size, small or large, x bar is perfectly normal with mean mu and variance sigma square over ns. This is case A. This case will help you both in sampling confidence interval for mu and in testing. All cases, in fact. I just summarize. If x is normal, sigma square is known. For any sample size, x bar is also normal. Case B. The distribution of x bar when the population is non-normal. The population is non-normal and sample size is large. Whenever population is non-normal, sample size must be large. Okay? This is the requirement. If samples are taken from non-normal population, For example, binomial, Poisson or unknown. Then for large sample size, n is greater or equal to 30, the distribution of x bar is approximately normal, and this result is known as central limit theorem. See, population is unknown or binomial or Poisson, but x bar is approximately normal. Why? Because sample size is large. So this result is known as the central limit theorem. Central limit theorem says for samples taken from non-normal populations and for large sample size, x bar is approximately normal. This is the statement of central limit theorem. And this is the way we write mathematically CLT. CLT for samples taken from a non-normal population, for example binomial, Poisson, unknown, with mean mu and variance sigma square. For large ns, ns greater or equal to 30, according to CLT, x bar is approximately normal. See, this is the statement of CLT. X bar is approximately normal with mean mu, variance sigma square over ns. Now see, all three, binomial, Poisson and unknown. Binomial, this is binomial with parameters n and p. So mean mu is np, see, mean is np and variance is npq. So for binomial, write in this way, x bar is approximately normal with mean np, variance npq over ns. See, this ns and this n both are different. This is the sample size, whereas this is the n of binomial. In case of Poisson, if population is Poisson, then mean is lambda, variance is lambda. Then write this in this way. X is approximately normal according to CLT, mean lambda, variance lambda over ns. In case of binomial, write in this way. In case of Poisson, write in this way. For large ns, x is approximately normal. For unknown, write in this way. Don't apply CLT if population is normal, whether sigma square is known or unknown. Example 1 of applications of CLT. See, the length in centimeters of certain type of snake is modeled by the random variable x. See, distribution is unknown. With mean this, standard deviation this, a random sample of 75 snakes is selected and the sample mean x bar is found. We need this probability. Since x is unknown and sample size is large, so apply CLT. X is non-normal, ns is large. This is the application of CLT. This is given, x bar is normal approximately according to CLT. This is mean, this is variance. 6.1 is standard deviation, square it and divide by ns. This is the formula of z. Now x bar, replace x bar by z. This 51 is here, 53 is here, mean is here, and under root of this is here. Now do it in the routine way as we used to do in S1. This is 5, this is 1 minus 5. Explain why it was necessary to use CLT in these solutions. Why? It was necessary because x is not stated to be normally distributed, or you can say x is unknown and sample size is large. Just write population distribution is unknown and sample size is large. This is the easiest way. just write X is unknown. The population is unknown. X means population. See, if population is normal, then never apply CLT. Don't apply CLT if population is normal. Since normal, straight away write X bar is normal, copy the same mean, copy this and divide this by sample size, which is 40. And just calculate this probability. Whether it was necessary? No, because population is normal. Example 2 of application of CLT. Okay. If the population is binomial and sample size is large, then number one, we have to apply CLT here. This is the application of CLT. Now, number one, find the approximate distribution of the sample mean. They are saying state the distribution of X bar. So, just 1 minute. See, population is binomial, sample size is large, so use CLT, and X bar is NPQ over NS. So NP is 2, NPQ is 1.6. So write 2 here, NPQ 1.6 over 160. Most of the students are weak at this concept. They don't know we apply CLT here. Find the probability that sample mean X bar is less than 1.8. This is here, mean is here, and this under root of this is here. Now this is small area, so 1 minus 5. Write your answer up to 3 SF. The answer is, I'm not sure what's the answer. Example 3 application of CLT. This is Poisson. See, Poisson size is large. So sample mean, we have to find sample mean is less than 2.88. So this is the application of CLT. So X bar is approximately normal. The population is normal. Poisson. This is the population. But since sample size is large, so apply CLT. X bar is normal. Lambda over NS. This is CLT. Now get this probability. This is here and the square root of this here. See another example. The times in minutes for which distribution? Unknown. Distribution is unknown. Has been this, standard deviation this. Another example of CLT, okay? Find the probability that Anjan's mean journey X bar 30 Mondays is between this and this. Since NS is greater or equal to 30, so and population unknown, and the population is unknown, so apply CLT. So X bar is approximately normal with mean mu variance sigma square over NS. Now easily get this. Convert this in Z. This 38.4 here, and this square root is here. The sample proportion. Sample proportion is very simple. Sample proportion is PS, frequency of requirement, divided by sample size. And for large ns greater than 30, let me write this here. For large ns greater or equal to 30, PS is approximately normal. Mean PS, this is PS QS over NS. Just remember this. I think this is in MF19 as well. We use this formula and this formula. Now, unbiased estimates, point estimates. This is the first formula of point estimate. If binomials P is unknown, we write P cap. This means estimate of P. This is PS, sample proportion. PS, sample proportion, and its formula is X upon NS, probability, frequency of requirement divided by sample size. This is the first formula of unbiased estimate. The second formula, unbiased estimate of population mean, sample mean, X bar sigma X over NS. If mu is unknown, get mu cap with the help of sample mean. Unbiased estimate of population variance, sigma cap square. It's ns minus 1 sample square, sample variance square. Where S square is this and this, both formulas are given in MF19. So if we substitute this formula here, we'll get this formula and this formula. Make sure you also remember assume mean method. So mean is sigma X minus A over NS plus A. We used to do this formula in S1, and variance square ns minus 1 sigma assume mean method. In June 25 you can find the question of this type. I did this question in my samplings lecture. Symbols used in sampling. Alright, this means true population mean. This means unbiased estimate of population mean. If true mean is unknown, then we find mu cap. Sample mean. True population variance. Unbiased estimate of population variance. And sample variance. Point estimates. So if P is unknown, then we find sample proportion, P cap X upon NS. We have done this formula. If true mean is population mean is unknown, then we find mu cap X bar sigma X over NS. And if true variance, population variance is unknown, we find unbiased estimate of population variance. We have done these formulas. A random sample of 100 values of a variable X is taken, and we have this data. We need unbiased estimates of population mean, which is mu cap, and variance, which is sigma cap square. So for mu cap, use X bar sigma X over N and get the answer. This is an exact answer, so leave it as it is. Don't round this up to 3SF. We leave exact answer as it is. Unbiased estimate of population variance. NS is 100, this is 99, sigma X square is given this number, NS, and mean, square of mean. This is non-exact to give your answer up to 3SF. Here we have a sample, so first get sigma X, which is 62.1. then get sigma x square. Sum of square of these observations will give you sigma x square. This is here. Do it in calculator and get the unbiased estimates. Population mean sigma x over n, and this is the formula of unbiased estimate of population variance. Find an expression in terms of A for the mean of these values. This is very simple, just add all and divide by 5. It is given that an unbiased estimate of the population variance using these values is 4. So this is given 4 is positive, we need the values of A. So this is very simple, value of A. This is the formula, ns upon ns minus 1 sigma x square divided by ns, mean square 4. Just solve this for A. Give a statistical reason why these estimates may not be reliable. When sample size is small, the accuracy of the information is not precise or not reliable. Small sample size, because of size of sample is small. Confidence interval. Before constructing CI, you must know the name of the population, about sigma square, whether it is known or unknown, and sample size, whether it's large or small. CI. 95% CI means we are 95% sure that mu lies in this interval. And these are the limits of CI. And we are 5% unsure. 2.5 means 5% unsure that mu does not lie in the interval. Confidence interval is variable. If we have different samples, then we will get different confidence intervals. This is the formula of confidence interval. X bar plus minus z times the standard deviation. Confidence interval for mu. This is the formula. Sample mean plus minus z times the standard deviation. So if we have this distribution of sample mean normal, then just write this standard deviation here. So x bar is here, plus minus z is here, and standard deviation is here. Sigma square over ns will become sigma upon ns. Wait a minute. Alhamdulillah. Now, how to find value of z in confidence interval? This is so simple. If the question is construct 98% CI for mu. See, this is 98%. So this is 1% and this is 1%. Now this total is 99% because this is 1%. Now just check phi inverse 0.99 in normal distribution table. It's 2.326. This is the way to find this value. 98% confidence interval limits in terms of z. Now case A, name of population, sample size, population variance. So confidence interval for population mean mu, case A. Let me explain these cases from this table because I have to discuss hypothesis testing as well. See, case A, population is normal, sigma square is known, sample size is irrelevant. When population is normal and sigma square is known, this is irrelevant, not important. Since population is normal, never apply CLT. Never. If population is normal, don't apply CLT. See, population is normal, so write X is normal with mean mu variance sigma square. Now distribution of X bar is normal with mean mu variance sigma square over NS. Just divide this by NS. Copy this entire, divide this by NS here and replace X by X bar. Case B, population is non-normal, sigma square is known, sample size is large. Now if you combine these two, then this is the application of CLT. This is not important. Whether it is known or unknown, we always apply CLT. This is blank. I left this place because I don't know the population. It's unknown. Okay, so because of CLT, X bar is approximately normal. Here X bar is perfectly normal. Here X bar is approximately normal. Mu and sigma square over NS. This is because of CLT. Case C is divided into two cases. Case C1, C2. Population is normal, population is non-normal. When population is normal, the chapter of CLT is closed. Never apply CLT. Now here sample size is large because sigma square is unknown. So when sigma square is unknown, sample size must be large. So X bar is perfectly normal. Population is normal, X bar is perfectly normal, and we use sigma cap square here because this is unknown. Now non-normal. Non-normal, sample size is large, so apply CLT. Sigma square is also unknown, so use sigma cap square here. Done. Now Z value. Z is X bar, this value is here, this is here, and the square root of this here. Same is here. X bar, mu, this. And confidence interval of these two. X bar plus minus Z, this is standard deviation. This is the CI of these two cases. And this is the CI, and this one is the CI of these two cases. See, all are same. Here we have sigma square, here we have sigma cap. You can also write this as, to make all of them similar, sigma upon under root NS. It was sigma square, so I wrote sigma. Now check this here. This is the formula of confidence interval, X bar plus minus Z times standard deviation. We don't apply CLT because of this. Since population is normal, so never apply CLT. And sigma cap square is here. Width is, if you multiply this by 2, you will get the width of confidence interval. And we use these things in hypothesis testing, Z-test. Please check this table carefully. Now, sample proportion. We did this formula earlier. PS plus minus Z under root of this. This is the confidence interval of PS, sample proportion. And this is the width. Multiply this by 2. Now let's go through some questions. See, the diameters x millimeters of a random sample 200 disk made by a certain machine were recorded. Population is unknown. So population is unknown, size is large, so application of CLT. This is case C2, the last case. So first get unbiased estimates, mu cap x bar sigma x over n. This is ns basically. So this is unbiased estimate of mean, this is unbiased estimate of variance, and this is the formula of confidence interval. X bar plus minus z sigma cap square over ns under root. Make sure you leave your answer up to 3SF. Gene choose 40 random samples and use each sample to calculate 95% confidence interval for mean, population mean. How many of these 40 confidence interval would be expected to include? Very simple, 95% of 40. 95% of 40 is 38. 38 on average, 38 intervals include the true value of population mean. Would be expected to include on average 38, just 95% of 40, and would not be expected 5% of 40. Two intervals on average do not include. Another example of the same case. I'm leaving this. Why it was necessary to use? Because sample size is large and population is non-normal. It's mentioned here. Non-normal, population is non-normal, sample size is large. I already have done this question. Confidence level. Again, population is unknown, sample size is large, C2. So unbiased estimates are here. Using this sample, the upper boundary of an alpha% confidence interval for the population mean is 26.0. We have two boundaries, like this one and this one, lower boundary, upper boundary. So upper boundary is given 26.0. So upper boundary, the formula is, this was the formula x bar plus minus z under root. So for upper boundary use x plus z under root. For lower boundary x minus. So h bar plus z under root. This is given. We have h bar, we have sigma cap square, we need z. So z is 1.747. Write this here and here. This is alpha%. So get this area, 1 minus 5, both areas are same. So alpha is 1 minus this and this. So 91.9%. Write this in this way. This is also fine, but the better way is this. Since it's alpha%, 91.9%, so just write alpha 91.9. Whenever you write alpha, just write 91.9. Don't write percentage sign. It is also accepted, but the better answer is this. Because this is alpha percent, this is 91.9%, so alpha is 91.9. Let me check important questions. Okay, population proportion. You should watch my lectures on sampling all questions, solutions of all 2025 questions. The link is in the, I will copy the link in the description. Confidence interval for population proportion PS. I told you for sample size greater or equal to 30, PS is approximately normal, PS mean, and this is the variance. So this is the formula for confidence interval for population proportion, sample proportion, sorry. June 20, question 5. Sunita has a six-sided die with faces these. The probability that the die shows a 6 on any throw is P. She throws the dice 500 times and finds that it shows a 6 70 times. So PS 70 upon 500. So this is PS, this is QS. 1 minus PS. Now we need 99% CI for P. Sample proportion. So PS plus minus Z, and this is the standard deviation. So PS is this. For 99%, get 0.995 value from the table, 2.576. This is here. Give your answer up to 3SF. Sunita believes that the die is fair. Use your answer to party to comment on her belief. See, if the die is fair, the probability of any number is 1 upon 6, which is 0.167. It lies in the CI. Her belief is correct. I repeat. If die is fair, then the probability of all numbers should be equal to 1 upon 6. Like 1, 2, 3. Each number should have this probability. So this is 0.167. Just check this number over here. This lies in CI. So her belief is correct. The die is fair. Now, she uses the result of her 500 throws to calculate an alpha percent confidence interval for P. This interval has width 0.04. This is the formula of width. Get the value of Z. And then alpha. See, Z is 1.289. Write this here, and get this area. This is 1 minus 5, 1.289. So this area is, this is not the area. This area would be something like, for example, A. This is A. This is A. So alpha is 1 minus 2A. So 1 minus 2A, 1 minus twice of this will give you the area. Let me write this here. Therefore, 1 minus 2A is equal to this, and therefore alpha is 80.3. This is so simple. Get this area, 1 minus 2 times this and this will give you this area. Then write alpha as 80.3. That's it from sampling. Now, the last chapter is hypothesis testing. I will do hypothesis testing after 2 minutes. Take a 2 minutes break. Hypothesis testing. Just let me just find the notes first, then we will take 2 minutes break. Okay, we will continue after 2 minutes. Alright, let's continue. An introduction of testing of hypothesis or hypothesis testing. Okay, hypothesis testing means a claim that we want to test or to test a claim. Important terms used in hypothesis testing. H0 means null hypothesis, the current situation. H1 alternative hypothesis, new situation, usually claim, not always. Alpha significance level, probability of critical region. Critical region means a region of rare or unique events, small probabilities therefore. Test value, X is always inclusive. Remember, test value is always inclusive. For example, 2 accidents per month, and if the test is a lower tail test, then X is less than or equal to 2. 10 shots out of 12, if upper tail test greater or equal to 10. So make sure you always take test value inclusive. If H1P is not equal, that means a two-tail test, and if X is small, then try the lower tail test. Do the lower tail test. This means lower tail. If X is large, then do the upper tail test. In two-tail test, I repeat, if X is small, then go for a lower tail test, and if X is close to N, then go for an upper tail test. H0. There are 3 types of testing. P of binomial, lambda of mu and population mean of continuous distributions. H1. H1 has three signs, either lesser, not equal, or greater. So H1 lesser sign means when look for a decrease in P lambda or mu. Not equal sign means look for a change in P lambda or mu. Greater sign means look for an increase in P lambda or mu. Here critical region is on left side. Critical region is on both sides. And for this case critical region is on right side. The upper tail test, H1 involves a greater sign. So critical region is on right side. This is the boundary of critical region. This probability is alpha %. Significance level. This is the region of rare events. And here we reject H0. If test value lies here, we reject H0. If test value lies here, we accept H0. Reject H0 means accept H1. Accept H0 means reject H1. But always conclude in the context of H0. Don't conclude in the context of H1. Otherwise you will be confused. I have explained this. If test value lies here, reject H0. If test value lies here, accept H0. Okay, if the H1 involves a greater sign, then find this probability. X is greater or equal to test value. In lower tail test, since lesser sign, so less than equal. In two tail, if X is close to 0, then go for a lower tail test. And if X is close to N, then go for an upper tail test, and alpha is divided equally. If alpha is 10%, 5% each. I have mentioned this here. If X is small, go for a lower tail test. Find this probability X less than equal to X and compare this with this. If X is large, do this, an upper tail test in two tail. You should watch my lecture on solutions of 2025 hypothesis testing to be good at this topic. Sumitra has a 6-sided die. She suspects that it is biased so that it shows a 6 less often. Less often means less than. She decides to test the die by throwing it 30 times. This is n of binomial. It shows a 6 on exactly 2 throws. This is the test value. Carry out the test at 5%. See, H0P is 1 upon 6. H1P is less than 1 upon 6, less often. Biased die, fair die. This sign means a lower tail test. Find this probability using binomial distribution. And then this probability is 10.3%. Now compare this probability with the given probability 5%. This comparison is compulsory. You have to show this comparison. 10.3% is greater than 5%. So 2 is outside the critical region. Therefore accept H0. And conclude in this way. There is insufficient evidence that the die is biased. Since we accept H0, so conclude in this way. Insufficient evidence that the die is biased. I'm leaving binomial questions to save time. Normal approximation to binomial distribution. See, in a game a ball is thrown and lands in one of 4 slots A, B, C, D. So the probability is 1 upon 4. Raju wishes to test whether the probability will land is 1 upon 4. So he wants to test whether it is 1 upon 4 or not. It's a 2-tailed test. These are H0 and H1. The ball is thrown 100 times. This question is of binomial and n is very large. So use S1's normal approximation. Using a suitable approximation, that is normal. This is NP, this is NPQ, and 2% significance level. Make sure you do continuity correction because you are using normal approximation. And it's a two-tailed test. Now observe the test value and mean. The test value is 15. In two-tailed test, you need to observe the test value in normal distribution, and mean is 25. Since test value is less than mean, then perform a lower tail test. Do this. Now use number line, get the continuity correction. 15.5 minus mu 25 under root. Now use normal distribution 1 minus 5. You don't need to do 1 minus 5 thing, you just need to compare this. This is z test. Minus 2.13. Now check this value. This is here. This is outside the critical region. So accept H0. Sufficient evidence that P is 1 upon 4. We accept H0, so conclude sufficient evidence that P is 1 upon 4, or you can conclude in this way. Insufficient evidence that P is not equal 1 upon 4. Poisson distribution in hypothesis testing. Here the population is Poisson. I am reading from here. Whether the mean number of accidents had decrease, lambda is less than. So this is H1. So H1 lambda is less than this. Lambda is equal. In H0 always put equal sign. Here copy the sign from the given information. I mean, just understand this. Decrease means lesser sign. So get the correct value of lambda. This is for per month, and here we have to do for 12 months. So lambda is 5.64. Lesser sign means a lower tail test. Test value is always inclusive. This is 2. Get this probability. This is 8%. Compare this with 5%. 8% is outside the critical region. So accept H0. Insufficient evidence to conclude that lambda had decreased. Normal approximation to Poisson distribution. Okay. The number of customers who visit a particular shop between 9 to 10 a.m. has distribution this. Past lambda was 5.2. Has increased, so greater sign. 20 days, this is per day. For 20 days, we are getting 104. Since lambda is greater than 15, so use normal approximation. So get the continuity correction through number line. This is the test value is 125. So 125 is here. Please see the fair solution. 125 is here. So 124.5. When we go on right, we take the lower bound. Now compare this value with the given value, this 1.96, 2.5%. This is here. So reject H0. Sufficient evidence that lambda has increased. Continuous distribution in hypothesis testing. Okay. An architect wishes to investigate whether the buildings in a certain city are higher on average. So one tail test, because look for an increase. in population mean. He takes a large random number of sample from the city and finds that the mean height of building in sample. He'll calculate the test statistic z test 2.41. Explain briefly whether he should use one tail or two tail. One tail because look for an increase in population mean. Okay, 1%, 99%, check the value in the table, it's 2.326. Now compare 2.41 z test with this value. This value lies here, so reject H0. There is sufficient evidence that mean has increased, or on average higher buildings in the city. Next question. This is a two-tail question. The mean weights of bags of carrots is mu kilograms, and inspector wishes to test whether this is equal to 2.0 or not. So our two-tail test, unbiased estimates. So first get population mean, unbiased estimate of population mean mu cap, then sigma cap square. Since population is unknown and S large, application of CLT. This is CLT. So this is mu naught sigma cap square over NS. Now check. It's a two-tail test. So check x bar is greater than mu naught. See, x bar is 2.15 and mu naught is 2.0. Then go for an upper tail test. Now compare this with this value, this one. So 1.565 is here. So except H0. No evidence to say that mu has changed. Now rejection region, critical region. Critical region in discrete distributions. In discrete distributions, use trial and error method. I have mentioned this here. Okay, the number of cars arriving at a certain road junction on weekday morning has Poisson distribution with mean this per minute. 2% fewer cars, less than 2 minutes. So get the correct value of lambda 9.2, less than sign H0 and H1. A lower tail test. Find the critical region. Well, for critical region, use trial and error method. First try with 2. Always try with 2. In lower tail test. Now the probability of 2 is 0.531%, which is less than 2%. So 2 is in critical region. Now let x be 3. Its probability 1.84% is still less than 2%. So 3 is in critical region. Now 4. This is greater than 2%, 4.86. So 4 is outside the critical region, hence this is the critical region. This is the way to find critical region in binomial and Poisson. Binomial. Same thing. Lower tail test, try with 2. It's 0.442, less than 5%, 2 is in critical. 3. This is greater than 5%, 3 is outside critical. Therefore, critical region is x is less than equal to 2 or 0, 1, 2. Now, critical region for continuous distributions. For continuous distribution, use this. Z test is equal to Z critical. I mean, write C here, mu naught here, and standard deviation. This is for population. And if it says alpha is 2.5%, then write its value 1.96, Z critical. Now this is very important. If C is A, if critical region is A, then write in this way. X is greater or equal to A. Please understand this carefully. See, critical region is A. So write X is greater or equal to A. This is the critical region in upper tail test. I have mentioned this here. Alright, in this question, it's mentioned mu is this, mu is less than this, and we have to do 2.5% testing. 63.5 is the test value. So 63.5 is here. We have all the values minus 2.115. Just compare this with 1.96. So this is less than, lies here, reject H0. Sufficient evidence that mu has decreased. Don't write mu, just write population mean has decreased. Now, Z critical. Use this. Z test is Z critical. Lower tail test, so write negative value here. C minus mu naught divided by standard deviation. This is the critical region. In lower tail test, write critical region in this way. This is here. Type 1 and type 2 errors. Well, a type 1 error occurs when a true H0 is rejected, and type 2 error occurs when a false H0 is accepted. Here type 1 error occurs because we reject H0 here, and here type 2 error may occur. Probability of type 1 is the probability of critical region. Type 2 accepted region. For type 2, a true value of P, lambda or mu must be given. New or true, both. New or true. Critical region for two-tailed test of discrete distributions. Trial and error is used. See, for C1, use lower values. Try with lower values, and for this, try with greater values. If n is 20, try with a value which is close to 20. The number of faults in cloth made a certain machine has Poisson distribution 2.4 per 10 meter square. 5% has decreased. So lambda is less than, and get the correct value for 30 meters square. Now find the probability of type 1. Probability of type 1 in discrete is probability critical region, and we find critical region with the help of trial and error method. So let's try with 2. X less than equal to 2 is less than 5%. 2 is inside the critical region. Now try with 3. This is greater than 5%. 3 is not in critical region, hence critical region is 0, 1, 2. So probability of type 1 is probability of critical, which is 0, 1, 2, which is this. That's the final answer. Okay, we have to perform the testing. 3 faults. Since x less than equal to 3 is this probability, which is greater than 5%, so 3 is not in critical region, so accept H0 and conclude in the context. Insufficient evidence that lambda has decreased. Now type 2. 5%, 30 meters square. Now new value of lambda. This is the new value. So get this value for 30 meters square. 1.5. Accepted region. Accepted region is x greater or equal to 3 because critical region is x less than equal to 2. Now find this probability with the help of this value of lambda. Same with binomial distribution. I am leaving binomial. Continuous distribution. This is the region of type 1 and this is the region of type 2. How to find in type 1 just write alpha percent. In continuous, probability of type 1 is alpha percent, and type 2 accepted region. we need Z test, critical value. This is a two-tailed test. There are two critical regions. So find both. For this, write the negative value. Z test is equal to Z critical, C1 minus mu naught divided by this, and equate this with this. For C1, use this value, negative value. For C2, use this positive value. 1.96. After getting C1 and C2, see, this is the critical region. C1, C2. So this is the probability of type 2, type 1, and this is type 2. For type 2, do this. See, critical region is this. This is critical region. This is critical region. So this is accepted region. And use this formula for critical region. Z test is critical. Okay, let's do this question. Let's understand this question. Well, we have 5.2 standard deviation. Mu is this. Mu is actually less than. So this is less than. In order to test his claim, he chooses random sample 100. Population is unknown, so CLT is applied because size is large, sample size. So get Z test. Test value, mean this under root here. Now compare this with 2.5% value. This lies here, so reject H0. Population mean is less than 64.6. Now we have to do type 2 error. What if they ask state the probability of type 1? Then type 1 would be alpha percent, 5%, 2.5. In continuous, just state alpha percent. Now for type 2 we need critical region, and this is the formula of critical region in continuous distribution. C minus, copy this entire thing. This entire thing is copied, replace this by C. Don't use this value here. We use this value in probability of type 2 error after getting critical region. It's a lower tail test, so this is the critical region. Critical region is XC less than equal to 63.581. So accepted region is this. C greater than. This is the accepted region. Now use 62.7 here, this new value. This is only used in the calculation of type 2 error probability. Now complete this. This is here. If you find this lecture helpful, do share it with your friends so that they may benefit from it. All the very best. Sallallahu alaihi wasallam. Ameen. Alhamdulillah Rabbil Alameen. Thank you for watching. Allah Hafiz.